I'm going to talk to you now about designing for concurrency using message passing. And Sean is right. There is a sort of undercurrent of safety in there. So you need to pay attention. So if we're designing for concurrency using message passing, then one question we're going to need to ask is why? Why are we using message passing? And so that's something I'm going to talk about. I'm also going to look at frameworks that you can use. If you're going to be using message passing, you're not going to just write everything in low-level C++. You're going to want to build something, have a framework around that to make it more straightforward. And then we're going to look at some design guidelines around the whole system for designing concurrency with message passing. And of course, in order to sort of really set in stone what this is going to make your overall system end up looking like, then I'm going to do some worked examples to just sort of generally so you can see what it's going to look, how things actually pan out in practice. So, why? Why would we use message passing?
Is there a chance that your microphone is not working?
Is the microphone,
Is the microphone working? It's not loud.
Okay, I can just speak louder, that's okay. So yeah, so the simple answer to why you might use message passing for your concurrency is because you can eliminate all your concurrency bugs. Yeah, I mean that's the simple answer, but it's not the whole truth. It's sort of an aspect of that. In reality, then you can get rid of explicit synchronization in your code, because if you're passing messages between places, then you can put all the synchronization in the message passing framework. And so the code that you're writing that's sending messages doesn't have to worry. You don't have to put any explicit mutex locks in your code, and or any use of other synchronization like atomics or anything. You don't have to put that in your code. That's the application code that you're writing. It all belongs in the framework. And so that sort of separation of concerns means that once you've got your framework sorted, you can remove the code, and because it's not there, you can't have bugs in it, in your application. And the second thing is that then you can eliminate, because you don't have you're not explicitly using synchronization primitives, then you can eliminate OS-level deadlocks and race conditions, because you can't have a double lock of a mutex if you're not manually locking the mutexes. The framework prevents that from happening. So there's real benefits here to actually using it. When I say it eliminates all your concurrency bugs, it's not just being facetious, a simple answer. It's saying if you actually use this property, then large categories of concurrency bugs do go away. We don't have the race conditions, we don't have data races, because if you keep your data separate and the only communication between your different parts of your application is via sending messages, then there isn't this shared data. You can't have a data race if you don't have shared data. But it's not free. There's a cost. There's no free lunch, and this is one of those cases. You actually have to design your code around the idea that you're wanting to take advantage of this from message passing. So you have to take on board that you are going to use the framework for all synchronization. It's all very well saying, well, we can use the framework for all the synchronization. We don't have to write mutexes, but we're going to anyway. Well, no, you've just lost the If you have to design your code and think, okay, this code needs to run set on a separate thread from that other thing, and it needs to share data. I'm going to do that by sending messages. You have to take that into your design ethos, the way you structure your program. If you end up having bits where you have a background thread that you spin up for a purpose and then you use other synchronization to get it, that part of your code is still going to be subject to all the usual concurrency issues. So if you can eliminate that, you can make everything message passing, then the framework can do the synchronization and you can get the benefits. But you have to take that on board as a design ethos. And likewise, you have to avoid shared mutable state. It's all very well saying, yeah, well, we've got message passing, but that message was a shared pointer. And so now both parts have got references to the same object. And so now, potentially, you've got data races and all the issues that go with it. So don't do that. Don't share state. Don't take the easy answer. If you want to make your message something that the message itself is small and it points to something else, use a unique pointer that at least only has the single ownership. So again, it's a way that you have to design your system. You take it on board. If you adopt the ethos of doing it this way, there is no shared state. The synchronization belongs in the library. We'll do our code that way. Then you get the benefits. You have to change your design approach to make this work. It's not a silver bullet. We do still have potential for problems. There's potentials for race conditions. You can have, just because there isn't a low-level data race, but there can still be races in terms of if you've got multiple things sending messages and you've got multiple threads, two things on separate threads send a message to the same third thing at the same time-ish, there is actually a race. Which one gets there first? Does it matter? That depends on how you've designed your application. Overall, you try to structure it so that it doesn't matter which other things send in which order. Because, but that's a bigger application design issue rather than a framework issue or a low-level data race issue. So Thread Sanitizer won't pick up that sort of level problem because as far as it's concerned, there isn't a data race, you've just designed your application badly. And so that's just a bug that you need to track. And likewise, you can still write in a deadlock if you really try hard enough. You can have two things that send messages to each other and in such a way that each of them is waiting for the other one to send a message back before it does any more work. Again, this is an application design level bug and not a framework level bug, or therefore not something that the tools will easily pick up for you. But again, this is just application design and thinking through the problems. But because it's message passing as a framework, then actually you can analyze this better yourself and spot these sorts of problems yourself without having to really look at all the low-level intricacies of what does the C++ memory model say. Because every bit of code that you're writing actually is still single-threaded. Each unit that is sending and receiving messages, whilst it's running, is running on its own thread and interacting with the message passing framework rather than actually directly communicating with other threads. And then we do have a new problem as a potential, and that is where you might get messages dropped. And this can particularly be a case if your messages have to go over some form of network. The poster child for this is UDP messages. UDP packets really, really are not guaranteed to get there. And so anything that, if the framework uses UDP as a transport mechanism, then there's a potential that actually really the data really does get dropped. But even if you use something that's a bit more reliable like TCP, then if somebody unplugs the cable, then the packets just won't get there however hard you try. And so you need to look at your application design and think about, how is your application going to respond if I send a message to something and then it doesn't do its job? And so, again, it's a new problem, but it's an application design problem. And anything which has any form of distributed system, then you're going to encounter, you have to think about this. If you've got things running on two separate processors with a connection between, what happens if that connection dies? That's a very real thing that you have to think about. So yeah, it's still not a silver bullet. Okay, so what about frameworks? What can we use? If we're doing a message passing, then we're going to want to build a framework. We want our application code to be isolated from that. So fundamentally, I mean, when I say message passing framework, then I'm thinking not just of a C++ library. No, I'm thinking the whole system that goes together. Tooling that can manage the delivery of messages and make sure that they arrive in the right place and facilitate you writing code that makes sure that transport is done correctly and the messages go to the right place and they're handled correctly. And this means that as an application developer, you can focus on the content of your messages. What is the information that I'm trying to transfer from here to there? And you can focus on the target. Where is this message going? What is its purpose? What is the recipient module that I'm intending to communicate with? And then, of course, you can also focus on the processing. What am I going to do when I get this message? And these are the important parts of your application. What is the data that it's processing? Where is it going? And what am I doing with that data? And to a large extent, that is just the core. That is what we all do when we're writing applications all the time, is thinking about what is the data, where's it going, how are we processing it? And if we can farm out the transport mechanisms to the framework, then that makes our job as application developers that little bit easier, because we've got more of our time to focus on the things that actually matter for the application. Realistically, nobody cares the method by which the data gets from computer A to computer B. What they care about is, does the car stay on the road? And things like that. So yeah, focus on the messages, not the delivery mechanism. So one way to think about this is that it allows you to divide your application into a series of microservices. Tiny little bits that receive messages and do some processing and then send some further messages somewhere, either as a direct response or to some other microservice that's going to do some more processing. And then the API for that microservice is entirely encapsulated in the sequence of messages, the messages that it receives and the messages that it then sends. People have built websites based on microservices, then that's essentially what you look at is what requests might I receive through HTTP, and then what responses am I going to send, and am I going to actually trigger some HTTP requests to other microservices? That's one way of building a message passing framework. So if you're looking at the designs of systems, then all the documentation and presentations and things on the way of designing HTTP-based message passing frameworks and microservices can also then be used to apply to when you're doing C++ level message passing, if you think of it as microservices, and that your API is about the messages. So one of the ways that our message passing framework is going to help us eliminate our concurrency bugs is by providing a guarantee of non-reentrancy. So that when your code is processing a given message, then you're not going to find that the framework is calling back into the same bit of code on another thread. So that then that piece of code can reliably know, I am single-threaded here. The data that I can access is just mine. And so you don't have to worry about synchronization. You might potentially guarantee that all the messages for a given microservice are serviced on the same thread, but it might not, depending on how you've built your framework or which framework you've pulled from a third party. Then you might find that it uses a thread pool underneath, and so though it guarantees that your given service only handles one message at a time, but it might turn up, and the first time it runs on thread 1 from the thread pool, the second time round it runs on thread 2, and then back to thread 1, and then over to thread 4, and so on. And it might be shuffled around between threads for each subsequent message. Or alternatively, the framework might say, yeah, no, you've got a dedicated thread. All messages for this microservice come on this thread. And obviously that's a framework level decision, but either which way, you get the same guarantee of non-reentrancy, that you're not going to have to worry about your code being called simultaneously on 2 different threads. And yeah, if things do guarantee a specific thread, then you might say, well, you can control which of the microservices do share a thread and which don't. That might be important that you have a dedicated thread for something that doesn't share with anything else, or it might not be. And depending on what level of control your framework gives you, then you might be able to utilize that, and that might be important. So you might also get a choice of delivery mechanism. It might be an in-process mechanism. It might turn out to be a simple function call, maybe through several layers, but might be a function call. Or it might be an in-process, a data structure, like a thread-safe queue of some description. Or it might be actually using network, sockets, or shared memory. There's a whole bunch of different mechanisms that you might use, and your framework may or may not give you a choice. Sometimes it's built in. You have if you use 0MQ for things, then the framework will make a choice of quite what mechanism you're using, and you don't actually necessarily know at the top, when you're at the code that's using it, what that mechanism is. You just know where your destination is. But fundamentally, what you're hoping is that the framework will mean that the code that you write in the application level is completely isolated from the choice of delivery mechanism. So you write the same code. It just says send message. And you specify the target, and you specify what the message is, and it just happens. Whereas at some level, at the top level of your application, then you're going to somehow have to make that choice. And whether that's a runtime configuration mechanism or a compile time mechanism, might vary depending on which framework you use, and whether you've written it yourself or, again, pulled in a third-party framework. But if you're using a framework, what you're striving for is that your application code doesn't know what the delivery mechanism is. It just knows that it's a message and where it's going. So that's all the theory, about message passing frameworks and design. But in practice, you've got to look at what your options are for what framework you're going to choose. And if you choose the widely available third-party libraries, then actually in practice you have to write a lot of boilerplate. And so you have to be prepared for that, and maybe abstract it, have somebody in your company who's going to write a wrapper library that fits in better with your designs. So you just need to think about that, and then you might need to have a fixed structure to your outer application that's going to have a message loop that's going to drive this third-party library. So yeah, abstract that library if you can. Possibly write a tool, pre-processor tool. That's, so you write a domain-specific language of some description that says, well, these are the elements of my system that I'm connecting with messages, and then have it pre-process that and generate generate the boilerplate code for you to overall make your application level stuff just that little bit simpler. So you're not spending your time writing the same 20 lines of code around every bit because that's what the framework says you have to. Okay, so that's the theory about sort of frameworks in general and message passing in general. What about specific guidelines for application purposes? First thing is focus. Think about what each of your microservice elements is intended to do. What is its purpose as an aggregate thing? Because it ought to have a single coherent task. You don't want to have a general sort of utilities microservice that does everything and calculates pi and opens files and tells you what Jim's birthday is. You carefully design the different parts. You have a service that's job is to tell you what the birthdays of your employees are. Have a service whose job is to manage files. Have a service whose job is to do complex maths. Split it up into fine-grained, focused microservices. And in doing so, avoid overlap. You don't want to split too far, so that you have a service whose job is to open files and another service whose job is to close files, and another one whose job is to read from files, and another service whose job is to write files. All those together belong in the file handling microservice, which will take a series of specific messages to deal with file handling, rather than having separate, disparate microservices, each of which only handles a tiny subset of the messages. But again, these are just general guidelines that apply all the time when you're writing applications. You want to have coherent modules which have a defined task and don't overlap with other modules. But when you're looking at things from a message passing point of view, then actually it becomes more significant about how you do this, how you divide things up, because we're striving for the no shared state between the different microservices. And then when you look at messages, we want value types. We don't want things that have shared references to all sorts of other bits around the system and that the message itself has behavior. We want a message that represents a value so that you can reason about it, so that you can copy it around. And when you take a copy, then that is an independent copy from the original one and not some reference to the shared bit of data that now they both access. And again, this has echoes of the safety stuff that Sean was talking about. If you have shared references to things, then that makes your job harder. So don't. And messages give us a discrete option for avoiding that. We have value messages. We are passing a piece of data from there to there. It is the name of something. It is a image of something from here to there. It is a block of data that I'm writing to a file or reading from a file, or a block of genome data that I'm processing, or whatever it is. But it's a discrete chunk of data that is a value type that you can copy around, rather than references. Because we are then relying on that lack of references to save us from our data races. We don't have to synchronize if we don't have shared references. And then avoid blocking. It makes the job of the framework that bit easier if it doesn't have to worry about a message handler blocking on some other thing. It goes hand in hand with the lack of synchronization, because we're not trying to do any synchronizing calls, synchronization calls being one of the main things that have blocking weights. And so don't do the blocking. If you need to do I/O, don't do blocking I/O calls. Instead, have a microservice whose job is to do the I/O for you. And then that service can then use the appropriate async I/O mechanisms to make sure that it can handle messages in a timely fashion. But your application code doesn't need to worry about that. It sends a request, sends a message to the file service, and then it handles a response message separately. Don't do blocking waits. If your microservice gets complicated, and if you divide things up, then lots of the time they won't be. They'll be fairly straightforward. I get a message, I do some processing, I send a response. Sorted. As they get more complicated, then you might need to keep track of complex state. I receive a message, I do some processing, I receive another message. It depends on the fact that I've received the original message, I've now gone a different state. As that gets more complicated, you might choose to opt for a state machine. But this is fine. We have essentially a single-threaded piece of code that has some data, and it receives events in the form of messages, and then changes its internal data. It's a classic state machine. And so actually, this is something that is really good, because as an industry, we know how to deal with single-threaded state machines. There is epic amounts of presentations, documentation, books, and libraries and things on the topic of how to do state machines. So you can take all that knowledge and use it in your microservice, knowing that you are a single-threaded state machine. And the events are triggered by messages coming in, but it's the same fundamental principle. Okay, so what does that look like? In terms of actually, as a concrete, if we're trying to have an application that deals with message passing, what can we do? So the first example I'm going to pull up is the classic dining philosophers problem from multi-threading literature. We have some number n of philosophers sat around a dining table, and these are philosophers. And so they are going to either eat or think, because clearly that's all philosophers do. And for some bizarre reason, they don't have enough chopsticks. They've got one each, which isn't enough to eat much. Trying to eat rice with one chopstick is going to be a really tricky thing to accomplish. Because in the classic example, what they do have is they have a giant shared bowl of rice that they're all eating from. And so they have, as well as not having enough chopsticks. And they all start with thinking. And then when they've done thinking, then they want to eat. And so they will pick up the chopsticks, and they will try and pick up two chopsticks next to each other. And if they can get both chopsticks, then they can proceed to eat some of this rice. And then when they're done, they'll put their chopsticks down. Hopefully they've wiped it off and cleaned it nicely so that the person next to them doesn't catch any cooties off them. But obviously this is a thought problem, so don't care about that. But if they can only get one chopstick, then they have a problem. They can't eat, and they want to eat, and they can't think. And you want to make sure that what we don't have is we have all the philosophers sat around the table, each clutching one chopstick, wishing they could eat. So we're trying to design a protocol by which our philosophers can manage to actually get chopsticks in pairs and put them down appropriately. And then obviously, so when they've been eating, they put down their chopsticks, they resume thinking, and then at some point they'll pick them up again. So this is the classic sort of problem. There are many ways of doing this. So this is but one of them. And the approach that I've chosen for this is that we can have an actor or microservice for each philosopher, another one for doing the I/O, because potentially I/O is a blocking thing, and just because you might want I/O. In this case, then our philosophers they're not going to talk directly, they're going to talk via the I/O service, but philosophers can be strange like that. We're going to have a service for timing, so we know how long they've been thinking or how long they've been eating. And then we're going to conjure up a new actor, a new microservice, the purpose of which is to manage the chopsticks, in terms of making sure that a philosopher either has 2 chopsticks or no chopsticks, and that we don't have a load of philosophers touching one chopstick and causing problems. So the I/O service is dead easy. You just wait for a message that says, print some text, and then you print some text. And if you're designing a system with microservices, then for message passing, you will end up with a fair number of tiny little services like this. They wait for a specific type of message. When they get their message, they do something specific, and that's all. And sometimes they might send a response back, but often they won't. There will be ones which, the leaf services, as it were, that sit at the edges of your system that just do something specific when you send them a message to do that. The timing actor is a bit more complicated, because you need to keep track of what the time is. And so the messages will be, and for the timing in this case, you send a message saying, notify me at a specific point. And then the timing service then stores that list of who needs to be notified and when. And then when the appropriate time elapses, based on some OS level timing mechanism, then it will then send another message back to the originator saying, here is that, your time has expired. In the simplest form, which is what we're going for here, then you just have a clock, which, so we specify the time and specify the target, and then that's all that's recorded. Alternatively, then depending on the system, then you might also stick some data in here saying, tell me that timer 3 has expired, or something like that, or some additional data to go with that timer, which is then just stored in the timer and then sent back. So for the philosophers themselves, our philosophers have 3 states. They are either thinking or eating or potentially waiting for some chopsticks so that they can eat. And in each of those states, then we're going to process the appropriate set of messages. So in our thinking state, then the only thing that we have to worry about when thinking is has our timer expired to say that we're done thinking. Because we're going to set a timer when we start thinking and output some text to say that's what this philosopher is doing. Now, in the waiting state, we're going to request some chopsticks because that's clearly what we're after, and we're going to output some text. And then when we receive the got chopsticks message, then we can start eating. And then our eating philosopher is going to set a timer to say how long he's intending to eat for, output some text to say that's what that philosopher is up to, and then when the timer has expired, then that philosopher can resume thinking. At which point, of course, then the philosopher will, of course, send another message saying that they have indeed finished with those chopsticks. So again, I mean, the handling doesn't have to be too tricky. When we start thinking, so this is like a state entry function where we've switched to the thinking state. So we're going to think for a random duration. We're going to send a message to say that we're thinking, and another saying, take the time now, add on our thinking time, and then send a message back to us to say that our time has expired. And then when the time has expired, then if we're currently thinking, then we send a message to say, we finished thinking, and change the state. Now we're waiting for chopsticks. And then again, then we have our state entry for waiting for chopsticks. Print out some text and send a request saying, can I have some chopsticks, please? I want the specific chopstick. There's my left-hand chopstick and my right-hand chopstick. And and this is me that's waiting. So, and you end up with lots of little bits of message handler code that change the state. And so on state entry, we send out some messages and then when we get a message, then we do some processing and potentially change the state. You end up with lots of little bits like this throughout your system. And each bit is simple, and you can look at it and clearly see, is this correct? Just by visual inspection. And that really helps for a lot of design. If you can see your code, it's all just there. Short functions, lots of people advocate short functions make things easier to understand. And writing message processing naturally leads to lots of short functions if you really break things down into tiny messages. So when we get our chopsticks, then we change to eating. It's lots of simple things. Eating, again, it's a random duration and a time request. So because we haven't put any data in our timer expiry messages, then our message handler for timer expiry is a little bit more complicated because we now need to deal with having finished thinking or having finished eating. So we have to do a state check. Here we've just got an if and else. If you've got multiple states, then you might actually then want that to be a switch case or potentially something else. But again, we just check what the current state. If we're eating, then we can hand in the chopsticks, send the return chopsticks message, and then change the state. Now we're thinking again. So lots of tiny little bits that put everything together. The microservice that deals with the chopsticks is probably one of the more complex parts of this system, actually, because it has state. That's more complex than just am I thinking or eating. It's like which philosopher has which chopstick? Are the chopsticks available for me to hand out? When a particular philosopher makes a request for some chopsticks. So when we get a request for some chopsticks, we have to check, are they available? And if they are, then we have to update the chopstick table to say, no, they're not available anymore. And then we have to send out a message back to that philosopher saying, yeah, here you are. You can have your chopsticks. And otherwise, we have to keep track of philosophers that have asked for chopsticks but haven't got them yet. And then when the philosopher hands in their chopsticks, they send the return chopsticks message. And so we have to mark them available. And then we have to process our list and see, are any of the philosophers that are waiting that we can hand back some chopsticks to? So if the chopsticks are available for a given request, then we can use the chopsticks in notify, which is exactly the same pair of lines of code here, except now it's the request element from the waiting list. So that's going to be an iterator, so we have to dereference the iterator. And then if we process that, then we remove the element, otherwise we just move on to the next one. So there's lots of, again, it's still not complicated. That bit of code still fits on a slide, and it's not in tiny font either. But that's partly because we have abstracting out separate small functions. So we're using chopsticks to mark the elements as in use, so they're not available. We have a list of are they free, and say they're false, and then actually send out the request to the philosopher that requested them, and say you've now got the chopsticks you asked for. So so that was one way of approaching the dining philosopher's problem. Hopefully, if you look at the slides afterwards, you'll be able to see that yes, it all does work, and that you can piece together, and you can look at a given the code for the philosopher and say, okay, yes, I can see that that is self-consistent, and then you can look at the code for the chopstick handling and say, yes, that's self-consistent, and you're not having to worry about the interactions between them in real time, as it were. Whereas if you're designing a standard concurrent system, then you've got to worry about when I lock this mutex, then what other threads am I going to be suspending and interrupting, and how that all interacts together. By just doing the messages, then you can look at each bit in isolation. So the second example that I've got is a robot control system. And this is sort of somewhat abstracted from a real robot control system that I did work on. So it's a lot less abstract than the Philosophers example. So if you have an industrial robot, then they often have a lot of motors and other actuators for moving all the very distant parts. If you've got a simple robot arm, for example, then it might move in multiple directions. And so you might have an actuator that moves it up and down, and one that moves it round, and one that rotates it, and moves the head at the end, and a whole bunch of actuators for controlling all the different parts. And you need to make sure that they all work in unison, in an appropriate fashion, to get the robot arm to move from over here to pick up the thing over there and put it over here. There's a whole bunch of coordination to make that happen. But we want to make it simple and easy to write, and where each bit is isolated so that the control mechanism for one actuator doesn't have to worry about interleaving itself with the control mechanism for one of the other actuators, which might use a different mechanism, or because it's a different type of hardware or something like that. So you want to make your robot control code as independent of the actual details of how each motor works as you can, and potentially have that running on over multiple threads. So in our system, we're going to have multiple microservices. We're going to have the central coordinator. Then we're going to have a controller for each of the actuators that control the motors for the robot. And then we're going to have another one for doing timing. So at the top level, when we have our central coordinator, if you need to move the robot to a specific position, then you're going to have a whole load of the individual position marks for each of the actuators. So you might have in order to move the robot arm to here, then the motor in the shoulder needs to be sort of 50% between lowest and highest, whereas the one for forward and backward might be 35% round, and the one for that twist is going to be a certain percentage round that way, and various open, and so there's a whole bunch of position markers for the overall where is that robot arm now. And so to move to a specific position, then you need to send a message to each of the controllers for each of the things, saying adjust that aspect of the robot position so it is that fraction through. And obviously, we set an overall state to say we're waiting for the position for this specific position. Then if we look at one of the specific actuators, then we get a message to say, can we change the position? And we tell the hardware, whatever you're doing now, stop. Lots of the hardware has, you just start the motor running and it keeps running until you tell it to stop and things like that. So whatever it's doing, stop the position so we can work out what's going on and change the new thing. We get the current position for the hardware, work out where we need to go, how far it is from where we need to go, how long it is that we've got to make that movement based on what the time was that we needed it to be there. And then if it actually needs to move at all, then we're going to start moving it and send a time request for when to stop. Because some of the control systems really are that simple. It's like start moving, and then it will keep moving until you tell it to stop in a certain 30 milliseconds later. And so you just do that. Other times, then you do have direct control, and you can say move it to position 7, because it's a stepwise actuator, and it knows whether it's on position 3 or 7, and you can tell it to move that. But sometimes you actually need to just say go, and then tell it, and then stop. So in this particular example, we'll do that. Start moving at a certain speed based on how long we've got to get there. We don't want, if we're trying to move the whole robot arm from here to here, We want it to go uniformly and steadily rather than go jerk and then move round and do a whole series of things. Because it makes the overall experience of watching it and processing it and dealing with it that much better if things move smoothly. Okay. So, and then obviously we have I said we send a timer request when we've got to the right position. So when we receive the timer request, then we'll tell the hardware to stop moving and then tell the controller that we've actually reached the desired position. There's a question.
Hardware stop moving. Is it a blocking call or?
Can you repeat the question?
Yes, so the question was this called hardware stop moving, is it blocking? Obviously that depends specifically on what the hardware driver does. And in the example system that I was working from, this was just they send a packet over the USB. And so it sends the packet to tell it to stop moving, and then the operating system and the hardware driver will actually make sure that it gets there in some point. So it's not a direct blocking call. But sometimes when you look at low-level hardware drivers, then you have no choice but to make blocking calls. But we try to avoid them where we can. Okay. So sometimes, though, when you're moving a robot, you don't want to just move it from here to here in a direct movement. There might be a reason why it has to go across and then up, because there's a thing in the way. And if you try and just adjust all the motors, then it goes clunk and something. And so you then program that we're waiting for position 1. So we move from here to here, and then we move to position 2, and then we move to position 3, and you do a whole series like this. Now this obviously is getting more complicated. We're building up a state machine, the different states that we're trying to be. But we have send messages to help facilitate this. And so you end up with a more complex state machine. We're waiting for position 1, which means that we've talked to all the individual actuators and we're waiting for them to reach the desired position for position 1. And then when we've got there, then we can send the position 1 reached message, which then moves us to waiting for position 2. I haven't duplicated the actuator messages to go with that, but there will be some. And then we reach for position 3. And so we send all the different actuator positions. And then eventually when we get to position 3, well, that was the end of our sequence. And so now we go back to idle and waiting for who's going to send us the next messages. So we're just, we're building up a complex state machine, but everything is just messaging. So, yeah, so if someone says trigger a full motion sequence, then we start by sort of, well, when do we need to be at position 1 in that motion sequence? And we're going to set the state, waiting for position 1, and then, send the first message to trigger things off. And then as each one comes in, then we need to process it. And again, in this case, we've got a switch statement, because there's going to be a lot of states, and we're waiting for position 1. Then we check if the actuators are there and send the messages and so forth. And obviously, as this gets more complicated, to start with, then a simple state machine designed using enums and switch case statements works fine. But as things get more complicated, then you're going to start reaching for state machine libraries and things like that. But again, it's still single-threaded state machine stuff. The fact that the events are triggered by messages is just sort of an implementation detail and is easily wrapped up to go with whatever state machine library that you use internally. And yeah, so fleshing that out some more, when we reach position 1, then we change the state to waiting for position 2, and then trigger the next move. So yeah, our state map can get large, and it did. In practice, then you end up with many, many states for a given robot, because it will have a whole set of pre-programmed movements, and those movements will have multiple stages, and you end up with a very big state map, and you need to have something to manage it. But yeah, we know how to do that. table-driven state machines is how we chose to do it, but there are many ways of doing that. But no, it's just classic single-threaded state machine stuff. So as an industry, we know how to do this. So just to sort of summarize where we've been, if you have a message passing framework or you put one together, then it allows you to design your application in terms of message processing and the messages themselves, rather than having to think about how that message got there. Lots of the time, if we're writing concurrent code, we actually spend a significant amount of our brain power thinking about how to get data from one part of the application to another, and communication mechanisms, because we're thinking about locking mutexes and setting semaphores and triggering condition variables, and we really don't want to be spending all that time thinking about that. We want to do that once, and then be done with it. And so that's what the message passing framework does for us. And even if we actually do have to develop it ourselves in-house, if you can map a third-party one, then that's good, because you're farming out that job of having done the thinking once to the third party. But that's what we're doing with framework, because that allows us to eliminate the explicit synchronization. In order to make that work and work well, we want our microservices or actors to focus on one task with minimal overlap, so that they don't have shared responsibilities, because if you have overlap and shared responsibilities, you end up reaching instinctively for shared state, which is a backward step. So that generally means that you've got your division wrong, and either you want to coalesce things or split them apart with a different boundary. Messages should be value types, again, to eliminate the potential for references and the shared references and the race conditions that can come from that. And then if you have things that would naturally be blocking calls, then move that to a separate service. And it might be that you end up with some low-level services that have nothing but blocking calls internally as options. But for the rest of the system, they don't need to worry about that. They sent it a message, it will happen at some point. And the fact that that message internally that microservice internally can only process one thing at a time because it's got internal blocking calls, that's mostly not a big deal. Because if you've divided things up as small as you can, then it's only going to be processing one thing at a time. Anyway, the fact that some of them might take actually take a noticeable amount of time due to blocking rather than anything else, not usually a big problem, particularly if you can isolate that. Give the blocking services a dedicated thread so that they don't cause a problem for everything else in your system. And then if things get complicated, we can use state machines to model stuff. So lots of you already know I wrote a book, C++ Concurrency Action, 2nd edition. At some point, I will finish off the C++ +20 addendum, and then it will be available as a free PDF. So that will be available. But now we have plenty of time for questions, I believe.